Hey folks, welcome to our final honors program colloquium for the spring semester 2021. As my dean calls it, the shortest, longest semester in history. I think that's probably fair. But we are very, very happy to welcome back someone who has spoken in the honors colloquium before, Dr. Greg Hogan, who's an assistant professor of chemistry here at A&M Texarkana. And today he is going to be speaking on It's a Trap, the capture of guest molecules within a hydrogen-bonded metal organic framework. And I'm hoping for copious Star Wars references. So I will turn it over to him to not disappoint us on that. Thank you.
All right. Thank you, Craig. I guess I will disappoint because those were the humorous things I was planning to do and got mixed up because I was even planning to even try to voice record and get, Admiral Akbar's voice every time I needed it, but alas. So appreciate the warm welcome and get my screen share. This is the one we're going to share. There we go. And let me few minor adjustments. This is going to let me to, there we go. All right. Figure out where I want to move everybody's picture. I guess let's go to the bottom. There we go. All right, got to organize myself. So as we saw what Craig mentioned for our title, our biggest thing is this is the kind of a review of what's going on inside of my research lab. I have a couple of our student workers here that's inside the video itself, that is within the honors program, and also one chemistry major. And a co-author on two of our papers was also present that just walked off. And again, another chemistry major with her that is going to be on hopefully one of the future papers that's going to be coming out shortly. Talking about more guest inclusion, another fancy term we'll use called intercalation within a hydrogen bonded metal organic framework. All right, so if I miss anything at the very bottom of the screen that you're looking at, excuse me, I'm sorry, because I put my picture to the bottom, so I might have to keep moving it back and forth. But our frameworks, our material, what we're working on are typically generally classified as they are layered materials. So layered in the sense that, as you can see, a repeating pattern, and give me a nod, Craig, you see my little mouse move? Yeah, okay, good. So as you can see within this layer, we have the repeating portion of our layer. And in between the layers right there, what's called the interlayer region, typically with a lot of layered materials, i.e. like here we have a basic example of a normal clay material. Typically can hold little guest molecules, water, sometimes cations, could be neutral molecules as well that will just reside right inside of that layered material. And we will use the chemistry, the nature of those layered materials to help us to decide what could possibly go inside of the interlayer. So as you can see, the layer can be held by these three things right here at the top. Could be covalent bonds, coordinate covalent, which is fancy for it's going to be a metal interaction. And then you could have some cases of hydrogen bonding. The interlayer can be ionic, where you can have the ions. Could be hydrophilic, which is water loving. And you can have hydrophobic, where it's water hating. So you can have something that might be more of a polar nature, which will be of the hydrophilic region. And it could be something of the non-polar, where would be the hydrophobic. And like I said, we can take advantage of these different natures of our layered material. Okay, why the heck do we do this? That's always the case. As you can see, another little layered material that we've made inside of our lab. The biggest cases of what we can see are these materials can be used as sensors. Now, sensors in the sense of it can be a photoluminescence that if we include a certain molecule, apply some energy, we may see light given off in a certain wavelength, get different colors depending on what molecule may be present. Probably the area where we're going to really focus on, that would be the neatest, but I wish I could for those sensors, but just don't have the capability at this time. But probably the two largest of our areas is the region of storage and separations. Storage, in a sense of, we get into a time of hydrogen storage, is very noteworthy in other gases, because somebody like hydrogen is very, very flammable. Trying to store it, transport it, sometimes could be very dangerous. A lot of these frameworks where we can include guest molecules like a gas itself actually reduces the flammability and the kind of the dangerous nature of that gaseous material. So we can store it inside the framework, transport the solid material wherever it may be, and we have reduced all of the risk associated with, say, transporting hydrogen gas. All right, separations. We have the ability that you can think of this as like a molecular sponge, that if you were, say, in one instance, say you're purifying a DNA sample, and a lot of DNA synthesis, they like to use benzene, an aromatic organic molecule. We can take this kind of material, place it inside of the solution mixture, and simply absorb the one substance from that mixture. So it's kind of, like I said, it's going to kind of sponge it up. All right, and we also have a possibility within the separations to be a more selective separations. So if you had a variety of what you call isomers of a molecule, so it's a molecule that is going to be exactly the same in its pretty much in all the atoms that are present, but in a different orientation. So just kind of think of like there's my hand trying to make a circlish, that you could probably have a group right here off the top, and then you can have one off to the side. Okay, but then another isomer maybe where you'll have one from the top and then one at the bottom. So it's just in different connectivity within the same molecule. Technically they're different, but overall they're generally roughly the same. All right, separations of those are typically very challenging because of that similar nature. And lastly, catalysts. So again, we know about a catalyst. It's just things that really speed up reactions. Cars, for one, have catalytic converters. That's in essence speeding up the process of the breaking down for the combustion of your engine and such. So we have them everywhere. Metals are beautiful in the sense that they are those perfect catalyst samples. Now, how do we investigate? Okay, everything that we are going to run is going to be analyzed, because again, we've got to make sure and prove it is what it is. So this is where all of our fancy instrumental techniques, what we call the analytical techniques, all the fancy instruments. The two biggest ones, the two largest areas that we're going to focus on is right here, number one, for the most part today, and a little bit of number two. All right, we do X-ray analysis. We use X-ray analysis. It's all sent off to College Station for the use of single crystal X-ray diffraction. And in some cases, we've analyzed our samples through what's called powder X-ray diffraction. Now, I'll show you some pictures, and almost the majority of our talk is going to be geared around X-ray analysis. We also can look at thermal analysis, that we can take our sample, heat it up, and we can actually determine a rough weight percentage of what's coming off of our sample, where we can get an identification of what may be present. And that's right here with this first one called the thermogravimetric analyzer, or TGA. Okay, and then you can see there's a list of some other guys that we could possibly use, but for the sake of what we're talking about today, 3, 4, and 5 are just not as important, but they can be. All right, so here are some crystals, because this is what our research is mainly geared around. We grow crystals. A few samples, all of these are actually all copper-based materials. They all got this lovely blue color. And you can see with this top right picture right here, this is actually a piece of loose leaf paper that's right underneath our vial. So you can kind of get a size range of how large these crystals really are. And in some cases, as you can see, these nice kind of little rectangular shaped, they could be squarish also, but the idea is that if they're nice and opaque right through, not many stacking crystals on top of one another, those are the ones we are looking for to analyze. And this one, I'm very hopeful. This is a very new one that I actually took this picture probably on Monday. I guess that's yesterday. But someone that I'm hoping to send off very shortly for Xray analysis. Okay, so we grow our crystals, we send them off, we analyze them, and we use this information to prove/disprove of our reactions. Are we making what we should? Now, here is an example of an X-ray analysis. So once I've sent the crystal off, it gets analyzed. This is all thanks due to our crystallographer himself down in College Station, Dr. Joseph Rabinskis. A lot of our samples, as you can see right here on this right side, this is the same picture, the same crystal structure. Now, my crystallographer has to deal with this ball of mess over here on the right-hand side. It's what's called disorder. Okay, molecules are like people. You sit in a chair, you're in lecture, is your butt going to stay in that chair that entire time? More than likely not. You're going to fidget a little bit to the left, to the right, move around a little bit. Okay, same thing. That molecule, even though it was shot with a stream of liquid nitrogen at about 100 Kelvin, okay, so that's like negative 173 degrees Celsius, right? Those molecules are still moving. All right, so he has to model this and actually place the atoms in a certain position so that we can get this beautiful picture on this left-hand side. Okay, so you got to think about these molecules. They are moving back and forth, left and right, whatever they want to do at almost any given point in time. So as we said, it's a lot of work due to him. All right, so the overall general scheme of things we are making these hydrogen bonded metal organic frameworks. So what we're doing is we're taking a metal complex, as you can see here in this synthesis, a nickel-contained dicarboxylic acid. So that's what this group is called right here on the end, the little peripheral regions. These are carboxylic acids. And we're going to interact it with two equivalents of an amine. So pretty much what we're taking advantage of in chemistry-wise is an acid-base proton transfer. The amine is basic. The carboxylic acid, obviously it's an acid. So it's going to take this little hydrogen right here and transfer it to this amine, what's called deprotonating. And this guy is getting protonated. And it generates in a crystalline form of this layered framework. Okay, our biggest thing that we're looking to do is, it sounds difficult and everything looks kind of chaotic, but it's actually a simple and stable framework. Okay, and that's the biggest thing, is that we want to make sure that it's simplistic in nature and it is stable, because if we're going to try to quote, quote, transport hydrogen or any other gases, it's got to be stable. We don't want it to decompose and then there goes our gas. Okay. Now, in some cases, we have to make some of our components. So that metal complex is not commercially available. So we do a little simple synthesis, as you can see here, just taking what's called copper sulfate hexahydrate, two equivalents of what's known as pyridine 2,4-dicarboxylic acid. Just simply mix it, dissolve these guys in methanol water, mix them together, and you get a nice powdery blue substance that's just going to fall right out of solution. And we just collect this like a filtration, just a basic filtration. And we have our metal compound. Now, the big thing with this metal compound is that because of X-ray analysis, we are going to take advantage of what is called a unit cell. Unit cell is the simple repeating pattern of our molecules. And I'm looking for an example, so I'm going to step away for 2 seconds. So I will use this little box here. I found something very quickly. So imagine this is like a crystal, kind of a cube. So we have our, kind of the X, Y, and it's Z. Okay, so what we're going to take advantage of is those same dimensions for our crystal structure, is that if we take our X and Y, we'll call it in crystallographic terms as A and B. So we'll turn it this way. And so here is this top now is our layer itself, the AB, and trying to find the exact point. There it is, this end. Right here, this distance from the top to the bottom is what's called the interlayer. and that's our C distance. So that's where we're going to put our guest molecules, is in between here, and our metal compound, our complex, is making up of the layer. All right, and what we'll take advantage of within crystals is we will take this unit cell and stack another one right on side of it, and it's going to aggregate into 3 dimensions. Okay, now we make our compounds, and then like we said, so we are going to start, here's the kind of the basic review. Some of the things that we have that was ongoing in our research lab. This is one of our first publications with our students here at Texarkana. Gavin Beach, our first graduate of the chemistry program. Bertrand Bisong was a biology graduate. All right, and so our first paper is we were looking into the inclusion of alcohol guest molecules into our copper-based metal organic framework. And as you see, this came out in 19, so this is pretty new. Some of the take-home messages, what this paper has told us, that if we were to take our copper complex, and now we've changed our amine and gave it this chiral-based, what's called an alpha methyl benzylamine, and again, taking 2 equivalents of it, so we're getting that same acid-base transfer, that we are generating this little crystal structure after we allow it to crystallize in solution. Okay, it looks great. But the problem is this is just the unit cell. So again, we need to be able to look at it and grow it in our 3-dimensionality. And once we do it, we find we have a layered structure. So as you can see, here's our metal complex forming a layer right here at the top, where you see my mouse moving. The interlayer region, here's one of our interlayer regions. And then again, here's the bottom portion of our layer. Now, this one looks different than some of the previous pictures because it actually formed what's called a bilayer. So as you can see, you have 2 adjacent layers right on top of one another. A little bit different than what we've seen. Very interesting, and we're going to come up with a little conclusion on this and a little theory later on. Okay, so but not a big deal. It's research. All right, but next thing is the fact that inside this crystal structure, we had no intercalation. So there's no guest inclusion. Okay, so this is just the methyl benzylamine that formed our interlayer, and there's no extra molecules. Okay, reason is we chose something that was very large when we tried to undergo the initial synthesis of our crystal. And so what we did was, okay, let's decide to kind of scale things back a little bit. And we ran the exact same crystallization process. And this time we chose to layer with, we went with a variety of what are called the alkyl alcohols. And so we used 2-octanol. Okay, it's a carbon chain that's of 8 carbon lengths long with an alcohol and OH group on the end, or at the 2 position. Okay, actually crystallized very beautiful. It was actually one of those crystals that I showed you from that one of the first slides with the 4 crystal vials. Okay, we got the exact same unit cell, which is good reproducibility. Grow it in 3 dimensions and looks a little different. All right, the difference is that now we actually have a guest inclusion inside of our framework. Now, this is what we call a non-coordinative. So meaning it hasn't bonded to the metal itself. Okay, that's fine, that's good. We still have the bilayer, as you can see right here in this middle section, right? We still have a bilayer formation, but we have now included our 2-octanol molecule. Okay, nice. Now, this is a thermal analysis. This is the TGA data. So we've taken our sample right up here, started from the very beginning at approximately about 20-ish degrees, started heating it, and up here in this green line is showing our weight loss, our weight percentage. And as you can see, the weight loss corresponding to the alcohol molecule that's inside. And as we heat all the way up to about 200, 220 degrees, And then we start seeing the decomposition of our framework, which is actually really good for a weak interaction framework, that it's withstanding up to 200 degrees Celsius. So that's very compatible with some of the widely known metal coordinated frameworks nowadays. So very promising. All right, so our second paper, and if Holmes here, if he's going wants to talk a little bit, he's more than welcome to join in. But this is a paper that was accepted last summer, right before COVID. Actually, COVID really got started. I submitted right there March 16th of 2020, and it was accepted in June 3rd of 2020. So this is the guest inclusion of, we went with pyridine. Now, why did we choose pyridine in this case? Well, we were using alcohols, and we found that we had a large amount of non-coordinative binding of our guest molecules inside of our framework. Well, the idea we chose pyridine is because pyridine has a lone pair of electrons, and it might have the possibility of binding to the metal itself, because there was an empty vacant spot onto our metal. Okay, possibility, so we'll see. Okay, so synthesis again, very similar. We didn't change much except for right here, we chose our first one, what's called 4-methylpyridine. You can see from the crystal structure, we got the same exact unit cell. And there is our, once we grow it into 3D. Okay, oh, shoot, I thought I had my circles. I guess I don't. Nabbit. Sorry about that. I thought I had the circles like the last time with animation, but as you can see where I'm circling right there, I know it's very difficult now at this point. So right in this region, right in this middle, those are the 4-methylpyridine molecules that are all aligned inside of the, of the framework itself. You can also see an alternating pattern of those those pyridines, because this blue region is the nitrogen. So you can see one is pointing forward and the second is pointing backwards. I did that backwards on the screen. Okay, so we got a repeating guest insertion. Again, not exactly what we expected. It was a non-coordinative guest inclusion. We were hoping because of the pyridine itself, it might be able to attach. And as you can see now where I'm moving my mouse right here, there's our metal. And this is where a empty binding site to the metal itself that we would hope the pyridine would attach itself. But alas, in this case, we didn't. Okay, now we did a wide variety of amines inside of this publication, and also what we've did inside the lab itself. We also chose, as you see here, T-butylpyridine, 4-T-butylpyridine. We went for a bulkier base, bigger alkyl. So again, this is in organic terms, this is a more electron donating group. So we're going to try to force to see, can we push the electrons to be more donating inside of the nitrogen itself? Okay. Went ahead, got the crystal unit cell matched exactly the same of what we expected, and grow it in 3 dimensions, and you can see now a definite difference. If you're paying attention, see, as you can see right here, there we go, the circle works on that one, of course. We do have coordinative intercalation, because right here, this is the 4-T-butylpyridine. One is attached from the top layer and one is attached from the bottom layer, and they're almost stacked on top of each other, taking advantage of some very weak van der Waals interactions because of their close proximity. Now, a lot of things we expected with this. Again, we chose the 4-T-butyl because of the electron donating ability. Possibly expecting this actual connection. I was actually expecting all of them to bind in this format, but alas, they didn't. But we still have our bilayer, as you can see with our layer stacking. The only difference, instead of being nice and what's called lamellar and more planar, it's kind of a step up a little bit. So a little bit different, but it's kind of expected because now you have a larger, bulkier molecule inside of our framework. So it's got to give a little bit of space. Okay, and so that's one of the biggest takeaways with all this is we have to have space. Anything you want to chirp in there, Hone, with all this? You're more than welcome.
I think what we found out during our experiments is that most of the copper frameworks form a bilayer instead of single layer like zinc does. So that's one of the interesting things that we found out, along with these coordinate bonding between the gas and the frameworks. Like Dr. Hogan said earlier, we tried varieties of pyridines, derivatives, and we only get our luck with tert butyl pyridine, I think, and 4-methyl pyridine. So I don't know if that has something to do with the symmetry of the molecules, but
yeah, and it's one of the points what he mentioned. That's actually one of a good eye, because actually I'm going to go back real quickly and I'll move it again. Sorry. So this picture I showed earlier is actually the exact same amine molecule. This is the methylbenzylamine, but as you can see, it formed a single layer. It wasn't copper. This was a zinc framework. So again, we're seeing kind of a discrepancy, and it's also a different crystallographer too. So, you know, A&M versus Mizzou, I don't know who do we trust at that point. Wasn't SEMO, Craig, so it's okay. So I know you knew that, Chris. He taught at SEMO. All right, so wrong button. All right, so again, we saw the possibilities now within our 2 papers that we have more examples of the coordinative intercalation with the pyridines, kind of what we expected because of the basicity of pyridine itself. Looked like there was a driving mechanism because of the groups that we chose onto the pyridine itself, forced its way to give us the coordinative intercalation. So that's pretty much the gist of those 2 papers that we had that has come out recently. Like I said, in this paper here, didn't get the actual, that's my electronic copy once it was submitted, but actually it technically got quote published in journal this March. So it's actually a fairly recent in publication, but it's been out electronically for almost a year. Okay, now our current projects, I know I saved it. I put an S on that this morning. Must have been before coffee. So our current projects and future work, like I said, we're going to have a few of these up here. And one of them I wanted to add on to this as well, but it's actually one of the more interesting projects. Just didn't have enough time to draw all these silly little molecules. They're taking a little time. So everything we've talked about has been placing amines as within our interlayer. So the next thing that got me thinking was the fact, well, can we grow this interlayer distance? Because everything we've seen has been roughly about the same kind of C spacing in the interlayer distance, roughly about the rough 13.5 to about 14.5 angstroms. So an angstrom is a 10 to the negative 10 meter. So, you know, very, very itty bitty. So, well, we decided to go ahead and can we synthesize? So can we actually make our own longer amines? Since, again, commercially available is the biggest kicker in the butt that we have to deal with. So taking advantage of a nice, simple organic reaction, this is what's called a condensation reaction. We took 4-methylpyridine and we reacted with what's called 4-nitrobenzoyl chloride. So it's what's called an acid chloride. So we're going to get the interaction right here. This is what's going to be the bread and butter of this reaction. Using a base catalyst of triethylamine. Our solvent was what's called dichloromethane at 0 degrees Celsius. We've got to keep it cool because it's one of those very highly exothermic reactions. I tried it at room temperature just to prove it, and man, literally it will foam and bubble right out of your container and you lose almost everything. So you cool it down, just ice water is pretty much good, and everything stays magically inside of your beaker. You don't make a mess for your lab coordinator to clean up. So see. Now, we were able to, once we have synthesized this molecule, we were able to crystallize it. I think Hogan actually was the one who was the winner on this one. Generated a nice crystal. We sent it off, analyzed it, and as you can see, this is our crystal structure from this reaction. So here is the pyridine molecule. This is where the amine would be located, the NH2 right here. And this is the portion up here on the top is from the nitrobenzyl chloride. So I have it in reverse. So this is the NO2 group. And down here, this is the oxygen that would be double bonded, but now it is connected to the nitrogen. So synthesis worked out perfectly of what we expected. Okay, but now this is an NO2 group. It's not an amine. Everything we looked at had to have the NH2 off of it. So NO2 groups, nitro groups are very easily, in literature and paper, they're very easily reduced down to an NH2. So that's why we chose a method that I have used in the past, reduction with palladium on carbon and this wonderful compound called hydrazine, component of rocket fuel. It's really bad bud is what I want to say. But again, you can either use dichloromethane or methanol as your solvents. And again, so the only change is we are converting these oxygen atoms to hydrogens. So it's a little reduction reaction. We were able to collect a sample. We've been able to recrystallize it, grow some nice looking crystals, and they have been submitted. I was told not last Friday, but the Friday prior, we were supposed to have Xray time in College Station for this sample, and I haven't heard anything yet. So I'm hopeful. So we're waiting for it, and until we get confirmation, we tried to use it a little bit with not much success at this point. So I guess we're just waiting for confirmation on our molecule before we really start pushing forward with it, because now we have a longer amine group, which would theoretically give us a more extended interlayer distance, which can start opening up for larger molecules as our guest molecules, or even multiple molecules, which would be a possibility. Okay, we've also have created another framework, another hydrogen bonded metal organic framework by now extending the amine. As you can see, we now have a 2-carbon linker within our amine, and we now have magically gone back and formed a single layer. Okay, so no more double layer. This is back from that original structure from the very, very beginning. Okay, so got us thinking, well, is it the amine itself that's giving rise to the change into the framework itself, which is again going to be a possibility. Didn't show it, but we've had a crystal structure also that Hogan grew that actually had the amine, the NH2 group right here, so it didn't even have any extra carbon atoms, and we generated a single layered framework as well. So is it the possibility of copper with respect to the kind of where we had a little V point, a little intersection point on our amine group that's giving rise to the formation of a bilayer because it needs the extra space? Highly possible. But that is one of the things that we are studying currently right now by investigating these different amine groups. Okay, so there's that. And then again, we have another possible framework that we're waiting on. This was being hopeful onto the slide itself with this last little writing. I was hoping to have them submitted yesterday, but I got tied away. This is actually those new crystals that have grown. So we are going to be probably tomorrow, these will be submitted to College Station, and hopefully we'll have a new hydrogen bonded framework. And the amine that we have chosen this time is what's called tyramine. It's very similar to the little structure we just got on the last slide. Difference is, as you can see at the tail end at the very bottom down here where my picture is, there's an OH group. So what could we expect within our framework? So I'm going to go back just because there's a picture. So just imagine here, it's going to be all the same, except for right on this very end, there would be an OH. So we would have the possibility of binding through hydrogen bonding with almost 3 different locations within the neighboring framework. Or there is possibility of flexibility right here into our molecule that it can actually fold or flip over. So we can also have another possibility of some sort of interaction right inside of our of the framework. So few possibilities that at this point we don't know. It's going to be really the winner is going to be whoever is the lowest energy crystal structure. Okay, so whoever's going to be more stable inside of the crystalline lattice is going to be the winner. And that's what we will find out once our crystallographer runs our sample. Okay, so and that's the one we're waiting on. And like I said, there was another, you can see conclusions, but we had another one that we were working on too. I know that Ariel was part of it within also some of these works that we were just talking about, especially with the synthesis that I was wanting to put on, that we were actually trying to make a metal amine so that our interlayer distance would actually have a second metal. So we would have the metal layer, and then we would have a metal interlayer. So generating what's called a bimetallic framework. So we are, again, waiting on the exact same thing. We have we believe we have synthesized the actual metal amine, and just simply waiting for crystals to grow, because that's pretty much our Achilles heel at this point, is some of our crystals can grow like the one I showed you from the picture that I took yesterday. I made those solutions on Friday and had nice crystals that grew in a matter of about 3 days. I have a mixed metal. Yes, it was Friday to Monday. I see your mouth. But the mixed metal ones, I have some that's been in solution for nearly 2 to 3 weeks. So they all of our solutions are different. Some may take very small amounts of time, some may be a little bit longer. And so that's pretty much, that's where we stand at this point, is usually playing a waiting game. Okay, so conclusions, as you can see, we have synthesized a variety of reliable, stable hydrogen bonded frameworks. We have been successful inside of the inclusion of our guest molecules via coordinative and a non-coordinative inclusion. So we also, and we have actually started this, we have started using other metal complexes that we have formed. So instead of being copper or zinc, we have created some nickel, cobalt, we have cadmium, all these wonderful metals that we're going to use as well. And then as you can see where my, right here at the bottom where I can't read, I believe it says that's the mixed metal frameworks as well. So, and there's some of our work, or some older pictures we have, and there's Hone and Gavin from our initial group, and then Mr. David Ames telling you it's supposed to be okay. Questions?
Okay, very good. Thank you very much. We do have a question in the chat from Kevin. You are welcome to read it, or I can read it dramatically for you. Either one works.
I'm trying to move all this.
Okay, well, I'll just read it and you can answer.
Okay.
He asks, are these frameworks similar to the idea behind the metal tree O2 scrubbers? Could these crystals be used to capture and or break down dangerous substances like the, quote, forever chemicals?
Yeah, that's actually one of the possibilities within the storage itself, that I wrote a grant for some Department of Energy money that some of these frameworks can actually be very suitable for encapsulating, these hazardous ions that might be byproducts from, say, nuclear reactors and such. So it is possible to get and encapsulate some of those molecules, some of those ions inside of the framework itself. And like I said, I actually have a different research project that we haven't been able to start here because the starting materials are a little bit costly, but that's actually what it's geared toward, is those encapsulation of those specific metal ions.
Okay, thank you. Any other questions before I ask the one follow-up I have?
Yeah, I think I have one. So these layers are between metal compounds. So we could have a layer of sort of copper and a layer of zinc, and then there is this framework in between. Is there conductivity between the metal layers or not?
Since it's a majority organic, I know a lot of papers that I've read from other scientists that have ran similar things. The more organic the framework is, the less the conductivity is. So if it was more of a metal halogen, a halide framework, then yes, you would have high level of conductivity. But since the framework itself is almost, I think the actual number 60, so about 1/6 of the framework is metal, so it's very low, so it's really not going to generate much conductivity. So that's the one difference between some of the previous work that's done with all this is a lot of them, the previous founders actually did metal halide work, and here that being more organic based on the framework is the biggest discrepancy.
So would this then have applications in semiconductors then?
It will. Some of the there are some projects that I've seen that they have, because of the layered nature, semiconductors, batteries. I know John Goodenough won a Nobel Prize recently that I saw him talk twice now. Actually uses intercalation in a different mechanism. Again, doesn't really use much metal organic. He actually has a little bit more metallic nature, but yes, definitely has battery potential and semiconductor potential.
And so if let's say the layer in between the metals was mostly carbon, that would be non-conductive, is that right?
For the most part, but again, it all depends on how the arrangement. So since our framework is free floating in between, if it was more rigid, then yes.
I see.
So because we do not have the rigidity inside the layer itself, that's why we probably also won't have high conductivity.
Okay.
Okay, excellent. Yeah, that was actually, I'd say, similar-ish to my question, which was about essentially, industrial applications and so forth. So, because I don't really understand the chemistry side of it too well, I get the basics. But anyway, any other questions or anything before we let Dr. Hogan out? Okay, in that case, let's go ahead and thank Dr. Hogan. Very well done. You can applaud in your whatever Zoom ways you want. And that brings to an end our spring 2021 honors program colloquium series. So we've had, like I said, I think 7 really, really interesting presentations over the semester. I'll go ahead and get this one posted up on YouTube, and you can watch it as many times as you like for free. The internet's great. And all right, enjoy the rest of the semester. Chrissy doesn't want to watch it again. Anyhow, thanks again, Dr. Hogan. Thank you, everybody who attended, and I'll see you all later. All right, take care.